Sourcing the materials was a struggle from the start, and working with very limited equipment made every step a battle. But in the heat of the moment, even through the clumsy mistakes, we managed to build an exceptionally high-quality machine. You might notice some manual drilling that looks a bit rough, but there is a method to the madness. All holes were deburred and deliberately drilled slightly larger than the bolts. This allows for fine-tuning the alignment later, using shims to ensure everything is perfectly square and precise. Installing the ball screws and linear rails on this 880 by 485 mm frame was a true challenge. Every single bolt has been secured with high-strength thread locker, bonding metal to iron, to ensure nothing vibrates loose during heavy operations. Just look at the length of the scantry. It's incredibly long and rigid, but I overlooked one detail. I ordered an SFU 1605 ball screw, and it arrived with the wrong coupling. In my rush to get the machine running, I decided to install it anyway, specifically on the longest axis. I didn't want to mess with the Y-axis since it's a dual drive setup that works in pair. The air cut tests and initial measurements turned out nearly perfect, with only some minor corrections needed. I should mention, I couldn't source the right material for the Z-plate in time, so I had to improvise. This is just a temporary solution and will be upgraded later. The work ebb is also improvised from various materials, all of which were cut right here on this CNC. It was a true endurance test. I pushed the machine harder and harder, increasing the feed rate from 1,000 to 3,000 millimeters per minute. With a 6 millimeters upcut end mill spinning at 12,000 RPM, as I increased the depth of cut, everything seemed perfect. I was really satisfied with the performance. Currently, the machine is powered by an ESP32 board, and so far it's doing a great job. But we will dive deeper into the electronics in one of the upcoming videos. For the work ebb, I created a sandwich panel, glued and secured with dowels. Between the layers, I drilled a grid of holes and decided to lock M6 nuts inside the sandwich, spaced at a 100 by 100 millimeters pattern. For the top surface, I used 8 millimeters hard HDF laminate, actually leftovers from the laminate flooring. It provides a very hard and durable surface for the CNC operations. After all those operations, I decided to run the final surfacing with the same tool. For this final surfacing pass, I set the stepover to 50% of the tool diameter. Cutting 1.5 millimeters deep into the laminate at 3,000 millimeters per minute put a lot of pressure on the machine. Everything seemed fine, but then I noticed the spiral coupling was stretching significantly under the tension. It was only a matter of time before it reached its limit. It snapped like ice. This coupling just wasn't built for that kind of load, but don't worry. I've already ordered a proper replacement, the same as the ones on the Y-axis. While we wait for the parts to arrive, it's the perfect time to share this first chapter of the build with you. Thanks for watching the first step of this journey. If you want to see the repair and the electronics setup, don't forget to hit that subscribe button. See you in the next one.